Hi, future scientists and safe car drivers. I am Atom. Join me in this adventure where we will unravel the mysteries of the physics of braking distance and delve into the crucial importance of responsible driving. How does velocity of a vehicle affect its kinetic energy? Before we dive into the mechanics of calculating a vehicle's braking distance, let us first grasp the impact of altering velocity on the kinetic energy of the vehicle. What type of energy does the car have as it is moving? Kinetic energy, of course. Ke is calculated using the formula Ke equals 1/2 mv squared, where Ke is the kinetic energy in joules, m is the mass of the object in kilograms, and v is the velocity of the object in meter per second. Challenge question. Determine the kinetic energy of a 500 kilogram car that's moving at a speed of 10 meters per second. Pause here and check your answer. Ke equals 1/2 mv squared. So in this case, it will be equal to 1/2 times the mass is 500 kilogram times the velocity is 10 meters per second. So we have to square that, so that's a 100. So that equals 25,000 joules. Let us see how changing the velocity affects the Ke of the vehicle. It is important to look for the pattern of the data in the table. The table has velocity in meter per second in one column and kinetic energy in joules in the second column. When your velocity is 10 meters per second, we just calculated the kinetic energy as 25,000 joules. Now, if you double your velocity, so you travel at 20 meters per second, then your kinetic energy becomes 4 times 25,000 joules or 100,000 joules. As you can see, when the velocity is doubled, the Ke is increased 4 times because v is squared. Challenge question. When the velocity is tripled, the Ke is increased blank times. And when the velocity is increased 4 times, the Ke is increased blank times. Pause here and check your answers. When the velocity is tripled from the original velocity, the new velocity is 30 meters per second. So the kinetic energy will be 3 square times the original kinetic energy, or 9 times 25,000 joules, which is 225,000 joules. When the velocity is quadrupled, the new velocity becomes 40 meters per second. And the kinetic energy will be 4 square times the original Ke. So the new kinetic energy will be equal to 400,000 joules. And that's because Ke is increased 16 times. Braking distance calculation. Now, let us transition to the crucial concept of braking distance. Braking distance is the distance a vehicle travels from the moment the brakes are applied until it comes to a complete stop. When you press the brake pedal, the brakes apply a force that opposes the direction of the car's motion. The displacement of the car still is in the direction of its motion, while the braking force acts in the opposite direction. So when you press the brakes, you do negative work on the car. Why negative work? This is because the angle between the braking force F and the direction of displacement delta D is 180 degrees. W equals F times delta D times cosine theta. Theta equals 180 degrees here. Cos 180 equals -1. So work done becomes negative. This means that kinetic energy is taken away from the car. The car slows down and stops. In other words, this negative work decreases the kinetic energy of the car. As the car slows and stops, the car's kinetic energy transforms into heat energy from friction between the brake pads, the wheels, and the road surface. The relationship between velocity, kinetic energy, and braking distance is described by the work energy theorem. According to work energy theorem, work done by the brakes on the car equals the change in the kinetic energy of the car. F times delta D equals delta half mv squared, or F times delta D equals delta KE. Here, F is the braking force of the car in newtons, delta D is the braking distance in meters, M is the mass of the car in kilograms, and delta V is the change in velocity of the car in meter per second. The braking force F of a car is dependent on many factors of the car and the road surface. Therefore, the braking force is not an infinite amount of force. There is a max limit to the braking force depending on the driving conditions, and a safe driver will be wary of this fact. The mass of a given car, m, is also a fixed amount. To reiterate what I just said, the braking force and mass are fixed values for a given car. So braking distance is directly proportional to the square of the velocity. Delta D is directly proportional to V square. Let us see how changing the velocity affects the braking distance of the vehicle. It is important to look for the pattern of the data in the table. So here we have a table with 3 columns: velocity in meter per second, kinetic energy in joules, and braking distance delta D in meters. The original velocity 10 meter per second, we calculated the kinetic energy of the car in a problem that we did a few minutes ago, was 25,000 joules. Let's say this car has a braking distance of 8 meters. If you double your velocity, your kinetic energy will be 2 square the original kinetic energy. So it will be 4 times 25,000, so that is 100,000 joules. Your braking distance also follows the exact same pattern. So it will be 4 times the original braking distance, so 4 times 8 meters equals 32 meters. When you triple your velocity, your kinetic energy will be 9 times the original kinetic energy, and your braking distance will be 9 times the original braking distance. So that will be 9 times 8 meters, or 72 meters. When you quadruple your velocity, the kinetic energy will be 4 square times the original kinetic energy, and your braking distance will also be 4 square, but this time times the original displacement. So 16 times 8 equals 128 meters. Here is the key takeaway. Kinetic energy is proportional to the square of the velocity. The braking distance is also proportional to the square of the velocity. Challenge questions. If you drive 2 times faster, how much more braking distance do you need? Pause here and check your answer. Twice the velocity means 4 times the KE. The braking distance goes up 4 times as well. If you drive 3 times faster, how much more braking distance do you need? Pause here and check your answer. Thrice the velocity means 9 times the KE. The braking distance goes up 9 times as well. A car of mass 600 kilograms traveling at a velocity of 5 meters per second brakes to a stop. The braking force of the car is 1000 newtons. Calculate the braking distance or the skidding distance of the car. Pause here and check your answer. F times delta D equals delta half mv squared. Or we can write this as F times delta D equals delta KE, which equals final kinetic energy minus starting kinetic energy. The final kinetic energy equals 0 joules since the car comes to a stop. Initial kinetic energy equals 1/2 mv squared, which equals half times mass 600 kg times the velocity squared, which is 25, which equals 7,500 joules. Since the braking force is in the opposite direction, the braking force here will be negative 1,000 newtons times delta D equals 0 joules minus 7,500 joules. The negative and negative will cancel out, so we get delta D equals 7,500 joules divided by 1,000 newtons, and that equals 7.5 meters. So the braking distance or the skidding distance of the car equals 7.5 meters. Understanding the physics of braking distance is pivotal for making safe decisions on the road. Remember, both the kinetic energy of the vehicle and the braking distance are proportional to the square of the velocity. So drive responsibly, stay safe on the roads, and happy learning. If you found this exploration enjoyable, remember to like, share, and subscribe for more exciting journeys into science. Thank you.